All right, on to the back. These are multi-part conservation of energy problems. And again, I'm breaking down each step that you could ultimately solve the idea of these other things. But I'm going to break it down step by step. So to start, how much is the spring stretched? Leave it on the picture with the variable you use it for. So the spring started out at 0.1 meters unstretched, and you did work on it to compress it to 0.02 meters. Now, compressing is the same as stretching. They're identical. If we have a spring that can, compressing it will add energy, stretching it will add energy, same relationships. So to get into this, how much has it stretched? Well, it was 0.1 meters unstretched, and then it was 0.02 meters stretched, so we get 0.08 meters. And I want to label that right here, right? This is the unstretched length. This is the stretched length. This must be 0.08 meters. And what is the stretch variable? With the variable you'll use it for. The stretch variable is x. That's what we use for stretch. We don't use s because it looks like a 5. All right, so if the 0.2 kilogram ball comes out of the plunger with a velocity of 12 meters per second, it has what kind of energy? If something has a velocity, it must have kinetic energy. Label these quantities on the picture. So mass equals 0.2 kilograms. Velocity of the ball here, v equals 12 meters per second. So now I've got a picture going of what this is like. So how much kinetic energy does it have? Well, I've got my equation for kinetic energy. EK equals 1/2 mv squared. And plugging these numbers in, we get 1/2 times a mass of 0.2 times the velocity of 12 squared. So my number there is 14.4. So what does that mean? Joules, right? Because it's an energy. That means that this ball came out of the plunger with 14.4 joules of kinetic energy. So how much elastic must the plunger have had when it was fully compressed? 14.4 joules. That's that conservation of energy idea. The total energy never changes. So if it comes out with that much energy as a speed, it must have had that much energy, as a elastic before it fired. So 14.4 joules. This elastic must also be the amount of, well, you could say EK, right? We already said that, EK. Also, the amount of work done. There's actually a third possibility here. It could also be the energy transferred. These are all true answers to these blanks. That elastic must have been how much work I did on the spring, and how much energy I transferred to the spring, and also how much kinetic energy the ball has when it comes off. So how much force would have been required to pull the spring back that far? All right, I see force, and I see the word spring. We've got an equation for this. F spring equals Kx. And I want to remind you again, if you are just watching this video through, please stop, work ahead, and then come back and look. F spring equals Kx, but we have a problem here. What's the K? It's not anywhere in our thing. And in fact, the next question is going to ask for the spring constant. So we must have to use, oh my gosh, the motion sensor lights just went off. Well, that was fun. The motion sensor lights turned off on my room. Okay, so how much force would have been required to pull the spring back that far? F spring equals Kx. But we don't have a K. So we need to use a different formula that has force in it. I only know of one. Work equals force times distance. So to pull the spring back 0.08 meters, we must have a work and a force times a distance. So what's the work? Well, it must be how much energy it has. So 14.4 equals, force is what we're looking for, times the distance of 0.08. So setting it up is everything. At this point, we just do algebra, and we solve for how much force is required. And we get F equals 180 newtons. So what's the spring constant? We need the answer. You need the ideas up here. The spring constant is in a couple of different equations, and we can do this two different ways. We can say F equals kx, and we can say a force of 180 equals k times, how much did it stretch? 0.08. Or we can use the E elastic equation, equals 1/2 kx squared, and we can see that E elastic must be 14.4, and that equals 1/2 k times 0.08 squared. These are the correct strategies. The problem here is that these actually do not end up with the same number. If you did this either way and you got an answer for K, 2250 over here, 4500 over here, Mr. Barentine messed up. The work on a spring actually cannot be done with force times distance because the force changes. As we stretch the spring more, there's more stretch to the spring. It requires more force. So the work would have to actually be done with the graph. And that's on the stem extension that we looked at. But basically it makes a triangle. So either of these answers is fine. The strategies are still legit, but this actually is not a legit question. We cannot actually use work to solve for the force required to pull the spring back that far because the force of a spring actually changes. So we'll move on. Strategy is still good. Look for the variables. Try to plug things in as you can. All right, moving on to this one. So please read what this says. It's a breakdown of what I'm trying to get you to do. So if I use a force of 25 newtons to push a baseball, mass of 1 kilogram, during my full windup and throw, 1.8 meters, how fast is the ball going when I release it? See the steps below. So you're not going immediately to that, but you could. What you'd have to do is use the idea of what you have. We've got a force. We've got a 1.8 meters from where I reach back to where I release it must be a distance, and we've got a mass. So we have the tools to calculate what? What equation has 25 Newton and 1.8 meter variables in it? Well, they are force and distance, so it must be work equals force times distance. Now, for non-springs, we can definitely use this equation because the force is constant. Force of 25 newtons the whole time. So work must equal 25 times 1.8. Relatively simple one. We didn't actually have to do algebra this time. So we've done 45 joules of work. So that number represents both the work done on the ball and the what of the ball. Well, it represents the kinetic energy when I release it. The energy that the ball has, the energy transfer is something else you could put here, but I want you to note this is the kinetic energy. What equation can answer how fast the ball is going? Which equation has speed in it? You always want to look back at your equations and find the right one. Here's V, okay? So we can plug V in. How fast is the ball going? EK equals 1/2 mv squared. Notice how I did not just write 1/2 mv squared. We have to write the whole equation. Because what we are going to solve for V, we have to plug in EK. What's the kinetic energy of the ball? Well, it's how much work I did on it. 45 equals 1/2 times the mass, which I got from up here is 1 kilogram. Sorry, I was a little bit off the page here, I realized. Okay, so EK equals 1/2 mv squared. Solve that quantity for V. 45 is our EK because it's the work done. Equals 1/2 times the mass, which is 1 kilogram, times V squared, which is what we're actually solving for. So 1 kilogram goes 1 times a number is just still that number. So we'll multiply by 2 to get this by itself. So we have V squared equals 90. And then we have to square root both sides to get rid of the square. It's a crucial, crucial step. So if you left it as the square root of 90, I would take that. But the number here is approximately 9.5 meters per second. So in these multiple steps, we went from the force and the distance to how fast it was going at the end. But it takes the steps. We had to calculate the work first, realize it's the energy, and then calculate the V. So number 11 is asking you, same start, but how high up would it go? Well, luckily, we already calculated the work done. The energy transferred must have been 45 joules. So how high up would it go? That's what kind of energy does it have as it goes up into the air? It has 45 joules of EG. And that's the highest it's going to go. Is at the highest point, it will have no more EK. it will be all EG. We studied that for the first test. So 45 joules of EG, and EG equals mgh. So we have 45 equals 1 is my G, 1 is my mass, 10 is my G, and my height is what we're looking for. Divide both sides by 10. 1 can just go away because it's just a 1. And we get a height of 4.5 meters. So we throw something up with this fast, it's going to go this high. If we put this much work on something, it's going to reach a height of this. We can use these energies to solve all these different things. Hopefully you can see how this would be useful in the real world. We want to launch something off a ramp. We need to know how much kinetic energy we need to see how high we're going to go. Comes up all the time. All right, so number 12 is fully on you. And I want you to try it before I move on. Try it using this step-by-step breakdown. Solve for what we have, solve for the energy we have, and then go to the energy that we don't have that involves the spring constant. So fires a 0.1 kilogram dart. That must be a mass. 35 meters per second. Seriously, pause this video and try this out if you haven't done this yet. The spring stretches 0.15 meters. Am I going to put distance here? No, because it's a stretch. So this must be an x value, the stretch. So what's the spring constant? Okay, so I've got m and v and x. None of my equations have x and m or v in them. In fact, they have k, which is what we're ultimately solving for. So we're going to use this, but later. We need the one with m and v in it. It fired the dart at 35 meters per second. It must have a kinetic energy. So Ek equals 1/2 mv squared. We always want to write that down. I'm making this video longer, but I'm doing it anyway because that's what's important. We got to write down our equation. Equals 1/2 times 0.1 is our mass times 35 squared is our velocity. So we punch this into our calculator. 35 squared, you have to do that first. I know I've said it a bunch of times, but it's so, so important. And we get a total of 61.25 joules. How do I know it's joules? Because it was an energy. So it's got to be joules. So I've got that far. I got that just from what we are given. And now it's asking what's the spring constant of my Nerf gun. So which of my equations involves the spring constant? We actually have two. There's F spring is kx or E elastic is 1/2 kx. Now I don't have any forces, but I do have an energy. So we're probably going to use the EE equals 1/2 k times x squared. Write down the equation. Write down the equation first, and then we can go through it. How much E elastic does the spring have? Well, it has the same amount of elastic energy that it did have kinetic energy coming out. They have to be the same. Where did that kinetic energy come from? It came from the elastic energy. So this 61.25 is right here, and that equals 1/2 times k. And what's the stretch? It's right here, 0.15 squared. And then you do algebra. We square first, multiply it by 1/2, divide both sides by that number, and we ultimately get 5,444.444. What's the units for spring constant? Again, look at the rest of the test. Find a spring constant somewhere. I gave you one over here. Units for spring constant is newtons per meter.